Greetings and welcome to another short lecture for statics for mechanical engineering students. This lecture will cover the equilibrium of forces. Now, we've already covered how to add forces up into resultants, and this is one special case, but a very important special case, of having a resultant that when you add up all the forces, they all add up to 0. So you could imagine three forces in a triangle like this, where we start down here and we add another one graphically, tip to tail there, goes up to here, and then a third one that comes down here, and we end up at 0. So algebraically, this looks like this. The sum of all forces is 0. However, when we do our algebra, we always break it up into components. So according to our formulas, carefully if you look at them, this can only happen if all the components are 0. So to have the equilibrium of forces, we have to have two things in two dimensions, which is the sum of all horizontal forces is 0. And as you can see over on this side, we have AX and BX and CX. AX is a positive, BX is negative, and CX is negative, and these horizontal forces add up to 0 in the X direction. And also we have to have the sum of all vertical forces to be 0. And we have a similar situation here, where we have AY added to BY, and then CY is negative, and these three come together and add up to 0. So kind of like the previous diagram that had three forces that eventually came around to 0, this is just showing the components. In a previous video, I showed you how to take four forces that are concurrent at this point and put them into a table with their magnitudes and directions, then find the components of each of the forces, then add them up into the components for the resultant. Then, using the Pythagorean theorem and our inverse tangent formulas, we can find the magnitude and direction of our resultant. Now notice carefully that these columns actually represent the summation of forces. So this column represents the summation of all the x forces to the resultant, and this is the summation of all y forces to the resultant. So if we have a resultant that ends up being 0 here and here, then we know that we have a system that is in equilibrium. What's more, if we were to add up the opposite of the resultant, so that this would be, say, positive 144, and this would be a negative 216 pounds. If we were to add all of these up with this additional force, we could call it E, that was equal to our resultant that had the opposite forces for its components, the entire force system would add up to 0. So what we're looking for is a force, such as the opposite of this resultant, that would make this system come into equilibrium. So we can find the resultant and then simply take the opposite of it. Or we can simply assume that the resultant is going to be 0 and find the force by placing it in the table here without values known, and then find the values. That's what's going to be next. So here we have another example, keeping it simple. We've just got two forces, one here and one here, labeled A and B, and started setting up our table with A and B and their magnitudes. Now let's look at their directions here. A is at 55 degrees, but it's with respect to the negative x-axis. We want to make sure that everything is with respect to the positive x-axis. So 180 degrees minus 55 degrees is 125 degrees. Now also look at force B. It is in the third quadrant, so both components are going to be negative. We also have to find the hypotenuse here, but this is a 5, 12, 13 right triangle, so that makes it easy. We're going to put in for our directions. A is 125 degrees, and B is a triangle of -5, -12, 13. Calculating out the components, we have AX equals A cosine theta A, 4 kilonewtons times cosine of 125 degrees gives us -2.29 kilonewtons. AY also uses trigonometry. So we plug in sine for the y component. And it's positive. B uses slopes, so we'll take B times the horizontal over the hypotenuse. B is 8 kilonewtons times -5 over 13 brings us -3.08 kilonewtons, and By B times the vertical of the hypotenuse is 8 kilonewtons times -12 over 13, 4.10 kilonewtons. Okay, now that we've got the components, just enter them in. Okay, well, what's the point? Where are we trying to get to? Well, what we're trying to find is another force, C, that we can apply to this concurrent force system that will bring it into equilibrium. And I'm just going to assume that it's going to be somewhere like this. Okay, it could be in the first quadrant, could be in the fourth quadrant, probably not in the second or third, but we're looking for C. We don't know how much it is, and we don't know the angle. But we do know the resultant of the entire system. If it's in equilibrium, then it must be 0. So I'm going to fill in this for C. We don't have anything else that we can fill in here. I'm going to put my double line at the bottom here, and here's my resultant R. I know my resultant has to be 0 if it's in equilibrium. My direction doesn't matter. There's nothing there. And these two have to be 0. So what I do is I look at this column and I recognize that this whole thing has to equal 0. This plus this plus this has to equal that. And the same thing for the y column. And you say, well, we can't fill in c. Well, we kind of can. It's just a variable. So cx and cy. And now I just have to write these columns as equations. The sum of the forces in the x direction have to equal 0. That's our resultant. And those equal negative 2.29 kilonewtons minus 3.08 kilonewtons plus cx, and all of that has to equal 0. So I'm going to combine terms here on the right hand side. 0 equals 2.29 plus 3.08. They're both negative. So we have 5.37 kilonewtons plus cx. Then I simply solve for cx, adding 5.37 kilonewtons to both sides, and cx equals 5.37 kilonewtons. Now I can do the same thing for the y column. Sum of the forces in the y direction equals 0. And we have, once I put the proper negatives in there, it should be a negative 4.10. So sum of the forces in the y direction equals 0, equals 3.28 kilonewtons minus 4.10 kilonewtons plus cy. If I combine terms on the right hand side, I end up with 0 equals negative 0.82 kilonewtons plus cy, and then adding 0.82 kilonewtons to each side and rearranging a little bit, we get cy equals 0.82 kilonewtons. So I can take these values and put them into where we had variables before, and cx is 5.37 kilonewtons, cy is 0.82 kilonewtons, and from there I can go back and use my Pythagorean theorem. So c is square root of cx squared plus cy squared. That comes out to 6.76 kilonewtons. Theta c equal to the inverse tangent of cy over cx Don't have to worry about adding 180 degrees here because Cx is positive and theta C is 37.4 degrees. I'm going to fill in the table to finish it off. And that is how to solve a very basic concurrent force problem in 2 dimensions, where one force is given at an angle, another force is given with a slope, and you just need to find the third force that will bring it into equilibrium. So putting these 3 forces together will give you a resultant of 0, which means that the system is in equilibrium. I hope this helps